Good evening. Today we're going to look at the Module 13 check, go over the questions and how to approach each one. Notice the diagram here of the star. It's 100 kilograms being pushed with 110 newtons in the positive y direction and 75 newtons in the positive x direction. The first one is, what's the acceleration of the star? In order to determine that, we need to figure out what the net force is so that we can set the net force equal to 0. In order to determine that, the star is being pushed with 75 newtons this direction, and we're going to go ahead and make the 110 newtons up this way so that we can make sure we have a bow tie triangle. And so in order to find this line here, it's a squared plus b squared equals c squared, and c is going to be equal to the square root of a squared plus b squared. So that way we can really detail out how to come up with that number. And so if we take a look at our calculator, a squared will be 110 plus b squared, which is 75 squared, and then take the square root of that. So 133.1 meters per second squared. So acceleration is 130. Oh, I apologize. It's not the acceleration. It is the net force is 133.1 newtons. To find then the acceleration, it is the net force is equal to mass times acceleration. Therefore, 133.1 newtons is equal to 100 kilograms times A. We simply divide by 100, and acceleration is equal to 1.33 meters per second squared. A lot of folks leaving off units on numbers. We need to make sure that those are included. Next, what is the angle? Again, we're just using trig, so our SOHCAHTOA. In the problem, we are given the opposite and adjacent, so we're going to go ahead and use the tangent. That's tangent inverse of 110 newtons over 75 newtons. So if we plug that in our calculator correctly, again, please make sure that you are in degrees. It is second tangent to get the inverse, 110 over 75. And so we should be at about a 55.7 degree angle. Question number 2 then says, from the previous question, the star initially was at rest and traveled for 10 seconds. So V0 is equal to 0, t is 10 seconds, acceleration, again, 1.33 meters per second squared. Initially at rest is going to give us an initial x position of 0. We are looking for the final x position in terms of the displacement. Notice we have no final velocity, so we're going to use our no final velocity equation. X is x0 plus v0 t plus 1/2 at squared. And thankfully, a lot of these values cancel out if we're initially at rest. v0 t goes away and x0 goes away. So x is 1/2 at squared. X equals 1/2 times 1.33 meters per second squared times 10 squared, 10 seconds squared. And if we finalize that, we end up with 0.5 times 1.33 times 10 squared. So 66.5 meters. Again, making sure that we have units on those numbers. Next question about a hockey puck with a mass of 0.156 kilograms is being pushed by a hockey stick over a patch of friction-full ice. The force of friction on the puck is 0.75 newtons. The puck is accelerating at 1.5 meters per second squared in the positive x direction. So first of all, we're going to draw a free body diagram for the puck in the scenario described above. So there is our puck. We have the force of the ice on the puck, which is also aka a force of friction. We have the force of the earth on the puck. We have the, again, force of ice on the puck, we're led to believe that that is a Newton's first law scenario in the y direction. And we have the force of the stick on the puck there. So that would be your correct diagram. What is the magnitude of the force that is being applied to the puck by the stick? So what we already know is that we have a positive 1.5 meters per second squared, which means we are accelerating to the right. Since that acceleration exists, we know that we have a Newton's second law scenario. If you recall, for our map, our concept map, we first drew the force diagram. Now we've determined Newton's second law, which gives us the net force is equal to mass times acceleration. Well, we can't use this because we are looking for a specific force, and that specific force is the force of the stick on the puck. So we need to write ourselves a statement that will detail out exactly what it is that we want to solve for. Well, the positive force of stick on the puck plus the negative force of the ice on the puck, and that is a negative force because we are acting to the left, is equal to the mass, which is 0.156 kilograms, and the acceleration, 1.5 meters per second squared. This is really easy to solve for because we know the friction, or the force of the ice on the puck, to be 0.75 newtons. Then it's simply just isolating out those variables. And so in order to do that, we take the 0.156 times the acceleration, which was 1.5. So we've simplified the right side. And then we just subtract negative 0.75 to end up with a force of the stick on the puck to be 0.984 newtons. Finally, question number 4. A student is standing on a scale on an elevator that is accelerating at positive 3 meters per second squared. The mass of the student is 55 kilograms. So if we are standing on an elevator on a scale and we are accelerating at positive 3 meters per second squared, we're led to believe that we are accelerating in the positive direction because that acceleration is positive. So if we're drawing a force diagram, we know the force of the earth on the student does not change. It's the force of the elevator on the student that changes, and that force is going to be larger. So again, we know that there's an acceleration, so that leads us to Newton's second law, which is equal to the sum of the forces is equal to ma. Down here, we want to know what the reading on the scale is. Something to remember. Scales tell forces. So that's like the spring scale that we use in class. Balances tell kilograms or mass. So we have to keep that distinction in mind. Otherwise, we're going to end up putting our answer in kilograms when it really needs to be in newtons. I'll put newtons here as a reminder. So again, we're led to believe that we're accelerating upwards. We know that we're in Newton's second law, so the sum of the forces is equal to mass times acceleration. And once again, we're looking for a specific force. So this needs to be detailed out even more. So we have the positive force of the elevator on the student plus the negative force of Earth on the student is equal to the mass times the acceleration. Well, we know this side. Again, the mass is 55 kilograms, and the acceleration is positive 3 meters per second squared. We also know the force of the Earth on the student. That's simply the force of gravity. And the force of gravity is mass times gravity, or 55 kilograms times 10 meters per second squared. So 550 newtons. If we plug that in here as the negative 550 newtons, because if we go back up here and take a look, the force of the Earth on the student is acting down, so that has to be negative. calculating out the positive force on the student caused by the elevator is relatively simple. Again, we take 55 times 3, and then we simply just have to subtract the negative 550, and that gives us a force of the elevator on the student to be 715 newtons. And now it's very clear that that number makes sense because the larger arrow is facing upwards. We're accelerating upwards. Therefore, the force on the student caused by the elevator has to be larger than the force of gravity on the student, which is acting in the downward direction.